the generalizations you can make, especially towards the end with the pumpkin seeds, which I know is stupid. It's stupid, right? Pumpkin seeds. But the RAID disks, not stupid. You know, the idea that your data in your My Documents folder, that you work, you know, you do your papers for school, you store them in your My Documents folder, and you trust that it's going to be there. Should you trust that it's going to be there? What's the chance that it's going to be there tomorrow? Give me a number. 99.9999999. A bunch of nines and a 4. Or 3, thank you, and a 3. Because the chance that it's not going to be there is 3% raised to the, do you remember? 6, close, damn close. There's 6 independent hard drives. 6 independent backup drives. And the only way you would lose your data is if all 6 of them failed. That's it. If all 6 failed, you lose your data. And that happens 0.00007% of the time. So as long as one holds, you're okay. And the thing about one, as long as one of them holds, as soon as one fails, they fix it. They replace it with a new one. So that's the beauty of it. So that's exactly why it's important. This is why they put more than one valve in nuclear reactors, more than one backup valve. Because God, if the first one fails, right? If that first one goes, the second one should stop it. And they usually put more than one backup valve. More than one backup valve. My buddy, a perfect example of how not to do this correctly, he used to use 2 alarm clocks. Well, it was one alarm clock that had 2 alarms. So he'd set one to music and one to noise. Or no, excuse me, one to noise and one to the beep. So he'd wake me up. He slept like a rock. So I'd wake him up every day. I remember waking up for his finals. Like, he's, the only reason that guy's a doctor is because I kept him out of bed. And hear me cook? Yeah, you're watching this. I woke up for all his final exams. He never would have graduated with his bachelor's degree. But I remember hearing that. And he's like, it's redundant. I got two alarms. I'm like, technically you don't. You've got one alarm clock, which means if the power goes out, you lose both your redundant alarms. And he's like, what? And I'm like, it's okay, you're gonna be a doctor, it's fine. Go, little boy, go. But that's the point of redundancy. Redundancy is a good thing. That's why we have 2 kidneys. That's why we have 2 kidneys, friends. Because if one fails, that's awful, right? Makes you wonder, what else do we have? What else do we in our bodies is redundant? Kidneys? I'm assuming eyes. Lungs? Right? I'm assuming, I know eyes are a beauty feature for us, but I'm sure that we have 2 in case we lose one. Lungs?
Intestines.
Intestines?
Yeah, you can remove a lot.
Wow. Just the length of it, I guess. Feet, legs, arms. We got a lot of symmetry, right? A lot of symmetry. A lot of symmetry. What else? What else? What else internally? Lungs and kidneys. Ovaries? There we go. Ovaries, twice as many eggs. Wait, does each one make an egg? Is that how it works? Yep. Okay, there we go. Twice as many eggs. Sorry. It's been a long time since sex ed. What else? Well, anyway, the point is that redundancy is important and you can actually measure it. The trick with it is, and I was talking to some students about this up in office hours, the trick with it is measuring what happens in between. So for example, it's very easy to ask the question, what's the chance at least one holds? What's the chance at least one fails? But it's a trickier question to say, what's the chance half of them fail and half of them hold? What's the chance 2 fail and 4 hold? That becomes trickier, and we're going to address that in class together. That's too much to do in a project, in my opinion. And my chicken flock actually does a great job of explaining that, I think, beautifully. So we'll do them starting next week. It's actually, believe it or not, it's a perfect way to explain the binomial distribution, which is actually what you guys were doing, believe it or not, in some of those questions. Does the seed germinate or does it not? Does the dry fail or does it not? Does the person have a tattoo or do they not? Most of those questions can be viewed as binomial. Either they have or don't have a characteristic. Does somebody like Congress or not? That doesn't seem binomial. Nobody seems to like Congress right now. But there's still 2 choices. There's still 2 choices that make it binomial. So, and we're going to spend a lot of time in that distribution as the course winds on. So anyway, but before we do that, I want to get back into what we were talking about last time, which was the idea of these distributions of probabilities. Because you could view what you did in that project as a distribution of probabilities as well. I just don't want to yet because it's going to seem magical how the numbers come about. I don't want magic. I want understanding. We'll hit that next week. So let's recap. Let's recap the idea of a probability distribution. Now, I mentioned there are going to be 2 kinds of them. There are discrete and there are continuous ones. And we're not going to mention we're not going to mention continuous ones for right now. I just mentioned them. I guess I'm a liar. We're not going to get into them right now. I do want to get into them. I want to get into the normal distribution. But we'll hold that for I'm thinking like week 8 maybe, somewhere in there. That's the more logical place for it to be rather than right now. So as far as this goes, I want to talk about discrete ones. Now we were doing a bit of a build-up last time to create our first discrete probability distribution, and we did it by rolling one die. Does everybody have a pair of dice in front of them? If you don't, let's keep passing those around. Thank you, Andre, if you don't mind. Everybody make sure you get a pair of dice. We're going to use those in a minute.
Yeah, right here? Okay.
It's just going to help you to understand the distribution we'll do.
Thank you.
So experiment number one, I actually had you guys, rolling a single die and keeping track of what happened, essentially what happened. And we did a beautiful little experiment. We collected all the data. I think we had more ones than anything else, but it was arguably not really more ones. It was just because of our small sample. And then we created, we created a t-table of our results, if you remember. Remember what was in the left column of that t-table?
X equals pips showing.
Absolutely. X equals your pips that we're showing. And originally I called this the frequency column, but eventually we called it what?
Relative.
Absolutely. And then eventually I renamed it to
Experimental.
the experimental probability. And then we added one more column at the very end. Do you remember? Just the probability column. We called it theoretical. We went all the way out to experimental. The thing had like 12 columns by the time we were done. I apologize for that, but it's fun to build it up from scratch. So we had the frequency column first, with your guys' raw counts.
Right.
Then the relative frequency column that we added to it by taking your raw counts and dividing it by whatever the number was, 170 or something. 100. Thank you. And then we went one step further and said, but theoretically, what should we have seen percentage-wise?
1/6.
Exactly. That's what I'm going to focus on today, is that theoretical percentage. Because, I want to come back to why. I want to call it P of X if it's okay. Because I want you to get used to that notation. It does not mean F of X like it was a function. It can. It just doesn't have to. It doesn't have to equal that. You can make an equation. I'll show you really quickly how you can make an equation out of it. But all you've got to do is realize these are labels. X is your, remember what we called it? A random, starts with a V. That's the one! Random variable. Why do we call it a random variable? Its values were 1, 2, 3, 4, 5, and 6. Why do we call it a random variable? Defined as something that somehow depended on chance. So why would the number of pips be a random variable? Why is it only somehow dependent on chance? Go ahead, Madeline, go ahead.
Because we could have rolled any one of those 6 numbers.
And you tied both of them in right there. When you throw the die, you don't know what you're going to get, but you do know you're going to get between 1 and 6. So it's somehow dependent on chance in that you're not going to get a 7, and you're not going to get a -5, or you're not going to get a 13, but you don't know between 1 and 6 what's going to show up. This column tells you how frequently you can expect each one. In this case, as you guys said, it was all 1/6. 1/6, 1/6, 1/6, the whole way down. What did you notice about the sum of those probabilities? Does that make sense? Good. Why does it have to add to 1? What do you think? In your own words, why does it have to add to 1? Okay, Gene. You're just moving. You're just moving. I'm sorry. You're moving. I'm like an amphibian. Please go.
You're only rolling one dice.
You're good. So, but does that 1 mean 1 or 100%?
100%.
100%.
Good. So 100% of the time, you're going to get, go Patrick. Good. 100% of the time, you're going to get between a 1 and a 6, which is pretty much mathematically what Madeline just said verbally, if you will. You know you're going to get between a 1 and a 6, and this guarantees it. There's one part I didn't really emphasize last time, and I think you guys assumed it already. They're mutually exclusive results. You can't get more than one of them at a time. If you could get more than one of these at a time, you'd have to adjust this, obviously. But that wouldn't make any sense. You can't roll 2 and a 3. The die's not going to pop up on its edge, and if it does, you have to throw it away, because they'll kick you out of the Vegas casino. Fair enough? Do you remember what the average number of pips was? I think we did this in class together, I'm not sure.
Average was 3.5.
We did average them! God damn. When we run the, now, here's the deal. Here's the deal. We also, oh, the heat's coming on. You can feel it. The windows are making it worse. All right. Sorry, hang on 1 second.
Teacher dog. You can hear him running down the
hat or something on there, like hang something warm over it.
You have a heater on you? That'd be phenomenal.
Oh,
This room is always like this. It's been a while since it's flip-flopped like it has. We'll just keep an eye. That should turn off now that I did that to it. Let's see if that works. It's interesting. I just read an article kind of related to the idea of heat. There was a science teacher, and like, thank you. That's wonderful.
Oh.
This is why
Peter
Instagram was
Cozy.
invented, for reasons just like this. There was a science teacher, like 6th grade, explaining heat to students, and it was in a northern Massachusetts town, and they were trying to get like, when you think of heat, what do you think of? And the kids said, hats. And then the science teacher was like, no, what kind of things contain heat? And the kids were like, well, hats and rugs and sweaters, because they associated these cold winters, putting a sweater on. The sweater is what generates the heat that makes you warm. Not that it's insulating your body, but it's just as soon as you did that, I thought of that art. I just read it last night as I was passing out. But it's just, I love that. That image is beautiful. Thank you, thank you. Hopefully that cut off. I don't hear it anymore. Okay, I don't feel the heat either. Okay, we'll try to keep it monitored. Anyway, average 3.5, to which people yesterday correctly proclaimed, you can't roll a 3.5. Exactly, you can't roll a 3.5. Of course you can't. But can you average a 3.5?
Yes.
Of course, because for every one that you roll,
You roll a 5.
you're going to roll a 5 or a 6. Can I go with 6 instead?
Oh, 6.
For every one, you're going to roll a 6, which averages to 3.5. For every 2, you're going to roll a 5, which averages to 3.5. And for every 1, or for every 3, you're going to roll a 4. Said a different way, and I'd like to explain it this way. I think this will be clearer for you. Remember how we did weighted means back in the day? I'm going to slide over this way. Now, I haven't made you do one of these by hand in a long time. And Angie, I'm not going to make you do it more than this once right here. But I think this explains beautifully. I like you. I'm going to do another one later on today. I think this explains in a beautiful way the idea of why the average is 3.5 and why it catches up, why the 1 catches up to the 7. So let's suppose we were actually doing the average of this distribution manually. Okay, back in the day. I'm going to call it mu instead of x bar, because I can. Why can I call it mu instead of x bar?
Because it's the whole population.
That's what happens. That's what happens on a fair die. It's no longer a sample like you guys took in class. This is what happens on a fair die. The average, if you remember from back in the day, is equal to the sum of the x times the f column. Remember that? But the f column is not called the p of x column, so if it's okay with you guys, I'm going to call that the sum of the x times the p of x column. If it's okay with you. Hopefully it's okay with you. Divided by, now back in the day it was sum of the f column. We have to add the f column up to see how many there were. The f column again is the p of x column. So that would be the sum of the p of x column. That looks terrible. It does. It looks terrible. So we can make it look more beautiful right now. Because one of those two pieces we can ignore. Because what's it equal to?
1.
One of those two pieces is equal to 1, isn't it? Isn't this equal to 1? Always. So really, to find the average of any distribution, and your TIs still do this, but I want you to understand exactly what's going on with that average. All you've got to do is take each data point, multiply it by its corresponding probability, and add all those up. Now, you know that because I made you do a GPA calculation, because I made you average that refused article from the Amazon. You know all that. But you didn't do it with percentages before. You did it with raw frequency counts before. I want to show you where the 3.5 comes from piece by piece, if that's okay. Piece by piece. So here's the deal. Here's the deal. Let's actually crunch each bit of it. The first x value is 1 times its probability of 1/6. Okay, we'll come back to that. The next x value is 2 times its 1/6, and 3, and so forth, times each one times their 1/6. Slide this over a smidge. Oh, that's actually in there. Now, what are the values of each of those things? Well, let's find out. That's a 1/6. That's a 1/3. That's a 1/2. That's 2/3. That's 5/6. And that's 1. But the simplicity of that mathematics belies. Danny, what are you thinking of right now? Go. What are you thinking?
It's just different
have to. We know what it adds up to. We know it's 3.5. We know it's going to be 3.5. John, help.
1 plus 2 plus 3 plus 4 plus 5 plus 6.
Divided by 6
Divided by 6.
is 3.5. Sure. But I want to make sure we focus on what each individual one of those numbers means. Because it becomes important later on when we talk about insurance policies and the payoffs for insurance policies. Here's what's going on. I know Danny's like, how does this tie to insurance policies? Trust me, it ties perfectly. It ties perfectly. This 1/6 right here is 1/6 of a pip. This is 1/3 of a pip. This is 1/2 of a pip, 2/3 of a pip, 5/6 of a pip, and 1 pip. Summed together is 3.5 pips. But why are all the fractions different? If the probabilities are all the same, 1/6, 1/6, 1/6, 1/6, 1/6, 1/6, you would think that these would all be equal to each other. But that's not true, because yes, they all happen with equal frequency, 1/6, 1/6, but the value they carry is different from piece to piece. So the 1/6 of a pip is only due to the fact that its face is only worth 1. This one's worth twice as much, because it's got 2 times as many pips on it. This one's worth 3 times as much. This one's 4 times, 5 times as much, and 6 times as much, which goes back to what John was just talking about, 1 plus 2 plus 3 plus 4. So when you break it down like this, which I don't have you do very often, honestly I don't. I will have you do it with the insurance policies because I want you to see the individual pieces of that. But what you're seeing is the value of pip that each individual random variable is contributing. Over time, the 1s contribute 1/6 of a pip. The 2s contribute 1/3, the 3s contribute 1/2, the 4s contribute 2/3, the 5s contribute 5/6, and the 6s contribute 1. So over time, they all contribute together 3.5 pips on average. Does that kind of ish?
Yeah.
It takes some more doing, and I might, that's why I lied to you when I said, Angie, we're not going to do it by hand again. I might have you do it by hand a few more times just to drive that point home even more, I think, and I do want to come back to that. But that's the idea of the average. Can you do it in your TI?
Yeah.
Of course, and we're about to. We'll do it in the TI in a minute with 2 dice. But I want to make sure that you kind of bought that first. Okay? Cool, let's change the experiment now. You got 2 dice in front of you. I don't want you to roll them just yet. I mean, you can if you want to. Go ahead, it's okay.